5.13 Exponential Growth and Decay Models. Alright, so we need to talk a little bit about some stuff that you're going to see in your science classes, particularly, but you will also see this in business classes and economics and that kind of stuff. And that would be exponential growth or decay functions. And they're usually in this kind of a format. Now, they don't end up looking like that a lot because the y's in the y sub 0 here is usually replaced with letters that represent something. So, but let's just talk about what this stuff stands for a little bit. So the y sub 0, that is the original, the O stands a little bit for the original amount of whatever we're looking for. So like bacteria grow exponentially. Money, if it's invested, grows exponentially. So that's the original amount. Okay, you can also think of this as what do you start with, the starting amount. Well, E is the natural base, we know that, so that leaves me with K. So K is just a constant. And, you know, if K is larger than 0, it's a positive, right? So then it would be considered a growth constant. So then the growth constant can take on many different shapes in terms of what it's named. We'll see that in an example coming up real quick. And if K is less than 0, then it's a negative, then it's a decaying function, so then it's a decay constant. Okay, and then T is time. T is time. It can be in hours, in minutes, in days, in years. It just depends on the function. So on word problems, on tests and stuff, I would give you part of this stuff. Now, I may not give it exactly to you. I may tell you, hey, we're going to start with 2000 as our original, and then you have to sort of figure things out. And sometimes, like in the first example, everything is sort of filled in for you already. They didn't have to do this, but it says, this is an example out of Business World. So if $2,000 are deposited at a rate of 6% compounded continuously for T years, the compounded amount in dollars on deposit is A equals 2,000 ERT. Okay, so they filled in the 2,000, so that is the starting amount, right? So there is your y sub 0. So if I'm looking at this as y is y sub 0, E, K, T, then the y sub 0 is the 2,000. So that was your y sub 0. They filled it in. Okay, so where does the 6% go? Well, 6% interest, that's an R. That's this R. That's the rate of return. The rate of return is 6%. Well, 6% is usually written this way. That's the K. In this case, R is K. The return rate is the growth constant because you're increasing the amount of money with 6% every year. So that's I can actually add that into this function. So I can actually write this as A equals, leave a little space here, is 2,000 E, the growth base, 0.06, and then it says for T years. So T here is defined in years. Okay, and the reason I said leave a little space here is because I would actually write this as a function of T now, because there's only one variable. So the amount, that's why they picked A, the amount after T years is given by 2000 E 0.06 T. Well, that's a function with one variable. So if it says find the amount in the count after 10 years, then you just find A10. And A10 would be 2000 times E and then 0.06 times 10. So the amount after 10 years is 2000 E. Well, that's actually it's going to be a calculator problem, isn't it? Now you can clearly do this one, or hopefully you can, so that's 0.6. But you're going to have to get a calculator here anyway. Okay, so here's a calculator. So we're going to do 2000, and then E to the exponent of, and why is this exponent not given? There we go. The exponent of, what did we say? 0.06 times, oh, and let's see how the times didn't go right there. 0.06 times 10. So this is my little scientific calculator. The answer is going to be $3,644.23. Okay, keep in mind this is money. So we actually didn't need this. We're going to just take the calculator answer for that. So the amount is $3,644.23. Rounded to 2 in this case because it's money. Okay, then B says how much interest is earned. Well, the interest is the difference between what you started with and what you have over here. So if we ended up with $3,644.23, then if you take away the original amount, then that is the amount of interest that we earned. So that would be $1,644.23. So that is the interest. Okay, and then the last one says, how long will it take for the amount of money to double? Well, if you start with 2,000, then doubling 2,000 would be 2,000 times 2, so that's 4,000. Well, that's the amount after an unknown number of years. So you can say, well, when do I have 4,000 if I started off with 2,000 and it grows at 6%? Well, you can solve this. So the first step would be to isolate the base. So 4,000 divided by 2,000, and then you get 2 here. And that is not a coincidence. Okay, that 2 is what doubling means. You always end up with a 2 here. It doesn't matter what this amount is. So you're solving actually this one, 0.06t. Okay, what I just try to say is that it doesn't matter what amount you start with. Let's say we started with 8,000 here, and we say, well, times 2. Well, 8,000 times 2 is 16,000, right? And then I would have had a 16,000 here, and I would have had 8,000 here, and then I would say, well, 16,000 divided by 8,000 is 2 again. So this question here, you don't need the original amount. If I say double, you know you're going to get a 2 here. Alright, so how do we solve this? Well, in this case, we want to get to the exponent, and it's a natural base, so we're going to take the natural log. So the natural log of 2, and on this side we'll get 0.06t. So that means the amount of time it takes to double is whatever the natural log of 2 is divided by 0.06. Okay, so back to my calculator. Let's clear this. I need to take the natural log of 2, and I'm going to divide that by 0.06. And so the answer is 11.55. So that takes 11.55, so just over 11.5 years, and that's it. Okay, here's a radioactive decay type of problem. And this one's definitely a little more complicated, so follow along again. It says 900 grams of a radioactive substance is present initially, so that is the y sub 0. And 20 years later, so if t is 20, only 450 grams. So the amount after 20 is 450 grams. How much of the substance will be present after 8 years? Okay, so this problem actually is you have to solve first and then solve again, and you'll see that here in a moment. So keep in mind that I would usually give you the structure of this, and so this is what the structure of an exponential growth looks like. So what do we have? Well, this y, that's the A20. The A20 is 450, so I can put the 450 here. The y sub 0, I said, is the 900, so there's your 900. The growth base is e. The growth constant, I don't know, but I do know that 450 is what is left if t is 20. So this is a one variable equation. So we're going to actually have to solve this equation before I even can start thinking about what happens after 8 years. So 450 divided by 900, now that's a half. So this is also known as the half-life, apparently then. If you get a half here, the half-life represents the amount of time it takes to go from a known quantity to half of that. And so we get e, and we'll write it this way. And so, again, that's a log. That will help us here. So the natural log will cancel on this side. So the natural log of a half will get you the 20 times k. So the growth constant is the natural log of a half divided by 20. Now here you have to be real careful. Okay. Now for us, I'm going to use a calculator and divide it out. If this was pre-calc, I would actually use this value over here because it's a little more precise. But if you plug this in your calculator, then you get a value, and let's see what we get out of that. Obviously you get a value. I'm trying to stall for a second. So the natural log of a half divided by 20, right? Okay, now you want to carry a good number of decimals here. So we're going to go 0, 3, 4, 7, because it rounds to 7 over here. So you gotta use a bunch of decimals here. If you just use a negative 0.03 here, your answer is going to be way off. Okay, so I would say you want to use at least three digits other than 0. So this first 0, these two first zeros to me don't count. So I'm just looking at 3 values here. So that's what I'm going to carry with me in terms of the amount of decimals. So negative 0.0, and then I said 347. So that's K. Well, how is that helping you? Well, now I can write this. I can say that the amount after T years is 900 E, the growth constant that I just figured out, and then now it's a variable function. It's a function variable in T only. So now if I want to know what happens after 8 years, I can get a calculator and just plug that in. And so if you plug this in and use an 8 here, you should get 682.07. And try to use a unit here. It's in grams. Okay, so that was A. Alright, so B says, exposure to the substance can have serious health consequences. How long will it take before there's only 1 gram left? 1 gram, that's the amount that's left. And I'm starting with 900, and I know I have a function that looks like this. And then there's your T. And again, so that's a one variable equation. You can solve this. So divide by 900 first. That gets rid of this. And then we have an exponential base of E. And so to get the exponent, to get the exponent down, we're going to take the natural log. So the natural log of 1 divided by 900 is equal to a negative 0.0347 times t. Notice that I don't figure out what 1 over 900 is. I'm not even putting this in the calculator. I am going to plug this into my calculator sort of in one step so that there is no more rounding than I need to. And then I'll figure out what that is worth, and then I'll round probably just a little bit. Okay, so what did we say? It said the natural log of 1 divided by 900. Make sure you close your parentheses here, and then divided by, and then it's a negative 0.0347, I think, 347. And this should be amount of time. It should be pretty big, and it's 196.0. So I'm just going to say 196 years. 196 years, 0.0 years. Showing that it rounds to 0 here by writing the extra little decimal. Okay. Last one. So this is a type of word problem that if I gave it to you on a test or a quiz, I would basically give you all of this. Okay. What I mean with that, all of it, is that this is a function that has some funky definitions in it, and so you're given those along the line, and then you have to figure out how to work with it. So it said Newton's law of cooling says the rate at which a body cools is proportional to the difference C in temperature between the body and the environment around it. So C is, it says here, C is the difference in temperature between the body. C is the body temp, whatever that means, and the environment temp. Okay, so the body, in this case, it looks like we're considering the body the gallon of orange juice. Okay, the temperature Ft of the body at the time T in appropriate units, so it just depends on what's given to you, is given by this function. And it does say that the constant temperature is the T sub 0. So T sub 0 is the temperature that the environment has if it's constant. So let's see what we have actually in the next part over here. So it says T sub 0 is the environment temperature. And I said that the C stands for the object temperature, or they call it a body temperature, the temperature of the body or the object minus the temperature of the environment. It says what? A gallon of orange juice with a temperature of 40 degrees. 40 degrees, that's the body temperature. Okay, that's the 40. Is set down in a room with a temperature of 7. The environment's temperature is 70. So the environment's temperature is 70. The juice warms to 50 degrees Fahrenheit after 1 hour. So what is that? So that is an f of t. This is the function after 1 hour gives you a 50. degrees Fahrenheit. And I can get rid of all the units there, so really don't need these. It's just, and the reason I can get rid of all the units because it said inappropriate units, so you ignore the units until you answer it again. So that's also something that I need to write over here. So the function, after 1 hour the temperature is 50. Alright, well let's fill in the function as they gave it to me. So f of t, that's the 50, is t sub 0, that's your 70, that's the environment temperature, plus c, well c is 40 minus 70, well 40 minus 70 is a negative 30, right? So this is a negative 30 e, and then it says a negative k, nobody said anything about a constant, and then t. Keep in mind that this here is a 1, this one here is a t, that's the time it took, so that's a 1, so I can plug that in. Well, there's a one variable equation, and I can solve this for k. So we just did this, but this is definitely a lot more difficult to sort of puzzle together. So I'm going to get rid of this plus here. It's just sort of making things difficult to read. 1 times k is k, so solve it. So subtract 70 on both sides. So I'm isolating my exponential base. I'm going to divide by negative 30 on both sides to get rid of that. I still have space. Yep. So e to the negative k is in, those negatives cancel, is 2 over 3. And then to get to the exponent, you need to take the natural log. And that will give you a negative k is the natural log of 2 over 3. And then hopefully I have a little more room. So that means k is the opposite of whatever the natural log of 2 over 3 gives you. And that gives me a k of 0.405. Again, notice I'm carrying 3 decimals here. I'm not showing you this one. I think we've done enough of these now. So plug it in. Make sure if you don't want to use the negative, just plug in ln 2 over 3 and change the sign. Okay, so that allows me to write the function. And the function is 70 minus 30, and then it says a negative. So this is 0.405. and that's supposed to be a negative k, then it's a negative 0.405 times t. Alright, let's see what they actually want me to do. It says, write an equation to model the data. Okay, well good, I just did that. So here's the equation. So that was actually A. So all this work just gives you an equation. And then B says, after how many hours is the temperature of the orange juice? 65. So the 65 is a function value after an unknown amount of time. So the 65 goes here. And now we're going to solve this one more time. And you'll see that we're basically solving the same structure that we just did. Except now we're solving for t, well previously we were solving for the growth constant. So subtract 70, right? So that's a negative 5. Negative 30, negative 0.405 t. And the negatives cancel. 5 divided by 30, which is 1 over 6, is, don't forget the e there, sorry, forgot the e. E to the negative 0.405 t. Take the natural log. Natural log of 1 over 6 will give you a negative 0.405 t. And if you plug that into the calculator, you get 4.42 hours. So let's see if you can figure this out, this last step, and work on your calculator skills a little bit. Thank you.